Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe. Lecture 23, Probability. To motivate the importance of probability in everyday life, throughout all professions, I'll use an example. There's a study done some years ago, I think back in the 80s, in which a study of medical doctors' use of probability was performed. The setup is that roughly in this age bracket that they looked at, roughly 1% of women would get breast cancer or would have breast cancer. Pretty low, could be lower. And they had a test, the mammogram, which had an 80% true positive result and I think a 10% false positive result. And when doctors put these two pieces of information together, the 1% and the 80%, they somehow came out with the probability that if a patient had tested positive from the mammogram, then they gave them a 70 to 80% probability of having cancer, breast cancer. But mathematically, that's totally incorrect. It's more like 7 or 8%. So you can imagine the trauma that these patients were put through because of these medical doctors and their inability to do basic mathematics. And so we won't actually cover the kind of statistics that are needed to analyze the cancer situation. That's called conditional probability, and you use something called Bayes' theorem. We'll get right up to it. So we'll cover basic probability up to the point where, like, we had 2 lectures in this series. The next lecture would be on conditional probability. But we're not going to do that. If you are interested in pursuing your studies in probability further, that would be the next thing to look into, would be conditional probability. To get started, let's use a simple example. And our example will be, a coin flip. Everyone is familiar with this. So you know that if I gave you the choice, pick heads or tails, you know what your chances of getting the right answer are, right? 50-50, right? So I flip it, call it. Somebody? You. Tails? Sorry, you lose. It's heads. So we'll use that as an example of how to set up probability mathematically. So the first thing that we need to talk about is what's called the sample space. And so I'm going to just write S for sample space. And I'm going to say that it's equal to, I'm going to use these curly brackets. And inside there, I'm going to put the set of all possible outcomes. Now, when I say set, that's a math term, but it's not much different than, say, a set of dishes or a set of silverware. It's a box that you put things of a certain item type into, and that's what belongs to the set. So in here, what belongs in the sample space set are all the possible outcomes for a coin flip. Well, you picked one of them, that was tails. The other one is heads. So the sample space consists of either heads or tails, and that's really all a coin can do, yes? So that's the sample space. But what we'll need mathematically is the size of that sample space, and so I'm going to use the absolute value symbols. You'll remember them from when we talked about negative. I think we talked about absolute value, did we? We may not have. That's kind of an algebra thing. But basically, if you had asked what's the absolute value of -5, the answer is 5. A lot of times people use it to measure like the length of things. So if they say here's a line, well, it may have some distance here in the horizontal and some distance in the vertical, and that would change as I rotate it, but the length of the thing always stays the same, right? So if it's a length-preserving type transformation that we're doing, then we would designate the length in a similar fashion as I'm doing the length of this set. But all you should read it as is this says how many elements are in that set. Well, we can count them. 1, 2. There are 2. So the sample space size is 2. Okay? Now, there's one other space that we're going to create here, and we're going to call that the event space, where an event is just something that happens. Like a coin is flipped and it comes up either heads or tails. But here we want to put in the desired event. So the desired outcome that we're looking for. And in that case, our desired event was a tails. Now the size of that space is the same as the size of the sample space in that it is the number of elements in the set. So the size of the event space here is just 1. Yes? So by definition, the probability is the size of the event space, the desired outcomes, divided by the size of the sample space. which in this case is just 1 over 2, which if we go back to lecture 13, decimal division, that's 0.5, which we could also write as 50 over 100, which is what we call 50%. So there's your 50% chances of getting heads or 50% chance of getting tails. Actually, I think I want to write it that way. I want to write probability, and I'll put just a T, T here for tails. So the probability of getting tails is equal to this divided by this, which is equal to 50%. Make sense?
Yeah.
Let me give you one to try. I'll put the definition of probability off to the side here for us. So the probability of an event, we'll do it like this, is equal to the size of the event space over the size of the sample space. So you're all probably familiar with die, with a die or dice, if there's more than one. That's the plural of die. From games that you've played, board games, it has 6 sides, as you can see, right? You just simply count the dots, and that will tell you what number you get. So this would be a 4, for example. And I want you to figure out, if I were to roll this die, what's the probability that we get a 3? So calculate the probability of rolling a 3. So you'll have to construct the sample space, you have to construct the space of desired outcomes, and use that to compute the probability. So go ahead and pause the video, try that at home, come back when you have your answer. All right, so we know that what we need is the number of possible the number of ways to get the desired outcome, and the number of ways that the dice roll can come out in the first place. So the first one is easy. The event that we're looking for is just this die coming up with a 3 showing. And the number of ways that you can get that, the size of that, is just 1. Now what about the sample space? Well, the sample space would consist of every possible face of the die, of which our desired outcome is one of them. And so the size of that space is 1, 2, 3, 4, 5, 6 elements. So now we have enough information to solve our problem. We just plug this in. For the number of possible desired outcomes, the number of ways to get the desired outcome, there's only one way to get it. And the size of the sample space is 6, so the probability is 1/6, which in decimal format would be 0.16 repeating, which is 16.7% if we carry it to the 10th place. Yeah? Good. So far we've only seen desired outcomes for which there's only one way to get it. But so let's look at a slightly different problem. Also with die, but let's get the probability of rolling an odd number. Right, so that's either the 1, the 3, or the 5. So we can write the event space as, we could get the 1, we could get the 3, or we could get the 5. So the size of that space is 3 elements. Okay, so 3 desired outcomes. So there's 3 ways for us to achieve our goal. Yeah. You can kind of see that there's a benefit to having more ways to achieve your goal, right? Yeah. That's just kind of intuitive. But the sample space size is still 6. So the probability of rolling an odd is just 3 over 6, which reduces to 1 over 2, which is again 0.5 or 50%. Okay, so that's not so bad, huh? So let me let you try calculating the probability of getting an even roll. So let me just clear out this. Okay, so you calculate the probability of rolling an even digit or an even number. So pause the video, come back when you have your answer. Well, it's probably not surprising that this is going to turn out basically the same. The event space, well, we could have a 2, we could have a 4, or we could have the 6 face turn up, and that would give us an even number. So there are still 3 ways to achieve our desired outcome here. Because if you think about it, every number is either even or odd. So that means that the probability of rolling even is, again, 3 over 6, which is going to be the 50% that we found before. This brings up an important point, right? Like I said, so every number that you roll is going to either be even or odd. There are no other possibilities. So you can say that the probability of rolling odd plus the probability of rolling even is equal to 1, or 100% if you want to do it in percents. And that makes sense, right? And this is a kind of a general rule for probabilities. If we sum up all the possible outcomes, the probabilities of all the possible outcomes, they have to add up to 1 or 100%. Okay? We'll circle back to that later and use that. But for now, let's consider an even more complicated scenario involving die, or actually dice. If I roll 2 dice, and I ask, what's the probability that the sum of the die faces add up to, say, 3 or 6 or 7 or something like that? What's the largest sum that we could get? Well, if I roll 1 die with a 6 and the other die came up 6, I'd get 12. And that would be the largest sum that we could get. What's the smallest sum that we could get? Well, this would have to be a 1, and this would have to be a 1, and so the smallest sum you could get is 2. Yeah? So the easiest way to construct all the possible outcomes for this die, or dice roll, is to make a table. So we'll put a 1, 1, 2, a 2, a 3, a 3, a 4, a 4. And we'll make a little table like this. So if both dies, this is the first die, and this is the second die. So if the first die comes up 1 and the second die comes up 1, the sum would be 2. If the first die was 1 and the second die was 2, that would sum to 3. And you can see what's going to happen here. It's going to count just up 4, 5, 6, and 7. Starting in the second row, if the first die comes up 2 and the second die comes up 1, we would begin at 3 and then 4, 5, 6, 7, 8. Here, 3 plus 1 is 4, 5, 6, 7, 8, and 9. 4 plus 1 is 5, 6, 7, 8, 9, 10. 5 plus 1 is 6, 7, 8, 9, 10, 11. And then finally 6 plus 1 is 7, 8, 9, 10, 11, and 12. And you can make a little more sense of this table of values if you first recognize the diagonal through here. This is the situation where both die come up the same, right? So both are a 1, you get a 2. Both are a 2, you get a 4. Both are a 3, you get a 6, right? And you notice that the upper triangle here, if you think of this as a triangle, is identical to the lower triangle. So the entry on the first row, 5th column, is a 6. And by symmetry, the entry on the 5th row, first column, will also be a 6. You see? So you can kind of see, here's the 7s that correspond. These 7s correspond. These 7s correspond. These 8s correspond. These 8s correspond. Here are the 9s. You see that symmetry there? Yeah. Well, I can simplify the information in this table by making a second table where I write the possible sums and the number of ways to achieve that sum, okay? So if I got a sum of 2, there's only one way that comes up, right? If I get a sum of 3, you can see there are 2 ways that that'll come up, yes? Yeah. So that we get a 2. And then for a sum of 4, we have 3 ways. A sum of 5, we'll have 4 ways. A sum of 6, we'll have 5 ways. And a sum of 7, we'll have 6 ways. 1, 2, 3, 4, 5, 6. Oops, I'm missing Oh, no, it's 6, sorry. 6 ways. And then for 8, it starts counting backwards again, right? So I'll put a comma and an 8 here because there's only 5 ways. 1, 2, 3, 4, 5. And then for a 9, there are 4 ways. For a 10, there are 3 ways. For an 11, there are 2 ways. And for a 12, just like 2, there's only 1 way, right?
Yeah.
Make sense?
Yes.
Now, the big question is, what's the sample space size for this double dice roll? You might say, oh, well, the sample space size must be, well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different possible sums, right? So is the sample space size equal to 11? And the answer is no, it's not. It's not equal to 11. And the reason why is because a sample space has to be, the outcomes in a sample space have to be of equal likelihood. Like with the coin toss, it was equally likely it comes up heads or tails. You see? If it was an unfair coin, say one that was like had a little bit of metal on one side or a magnet or something like that, such that it came out 90% heads and 10% tails, that would not be equal likelihood. And so that would not constitute a sample space that you can use probability for, okay? Just like this. I can't use these 11 different possible sums as the sample space because they're not of equal likelihood. It's much more likely to get a 7, sum of 7, right? Because there's 1, 2, 3, 4, 5, 6 ways to get it, than it would be to get snake eyes. That's rolling, each die has a 1 showing, okay? So what is the proper sample space size? Well, we can use our knowledge from the previous lecture in combinatorics to figure that out. We've got 2 coins, and so we say, okay, well, how many different choices do I have for this? Think of the ice cream, right? How many flavors do I have for this scoop? Well, it could come up 1, 2, 3, 4, 5, or 6, so there's 6 choices, right? Now, what about for the second die? I also have 6 choices, right? So we know that the number of ways this can come out is 6 times 6, which is 36. Yes? Alternatively, what we can do is we could write all the possible sums like this. Okay, so we'd write the 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then how many ways can I come up with a 2? Well, there's only 1 way. And I'll add to that the number of ways I can come up with a 3, which is 2 ways. And add to that the number of ways I can come up with a 4, which is 3 ways, plus the 5, which is 4 ways, plus the 6, which is 5 ways, plus the 7, which is 6 ways, plus the 8, which is back to 5 ways again, plus 4, plus 3, plus 2, plus 1. If I add up all of those, now I get the right sample space size. But you see what it's doing, right? I mean, it's really just telling you how many entries are in this table, right? And there are 6 times 6, or 36 entries in this table. So when I add all this up, this will add up to 36, of course. Yes?
Yeah.
So let's just write that the sample space size is 36. So let's do an example. What's the probability that I roll something that sums to 7? Well, we know that the sample space size being 36, we'll put that in the denominator. But what is the size of the possible outcomes? Well, if I just list them to roll a 7, I could get the first die, I'll write it like this. Not the size of, but just the space itself. We could get a 6. So 1, 2, 3, 4, 5, 6. And I'll put it in like this. And a 1. That would give me a 7. I could roll a 5 and a 2, etc., etc. You see where this is going, right? I'm just simply constructing it by this table, right? How do I get a 7? I can have a 5 and a 2, or a 4 and a 3, 2 and a 5, or 1 and a 6. Yes?
Yeah.
So if I look at this, it tells me that for 7 there are 6 ways. So the size of the event space is 6, which means that the probability of rolling a sum of 7 is 6 over 36, which is just 1 over 6, which is, again, that 0.16 repeating, or 16.7% that we had at the beginning when we talked about rolling a die, yeah?
Yeah.
Rolling a sum of 7 with 2 die is the same likelihood as just picking any random number on a single die roll, okay? All the other sums will be less likely, you see. So let me give you one to try. What is the probability of rolling 2 dice and getting a sum of 5? So pause the video, try that now. Come back when you have your answer. Well, again, we'll still have the same sample space size, so we can keep that in. But the events, right, what are the ways that we can get 5? Well, we could get a 4 and a 1. We could get a 3 and a 2. We could get a 2 and a 3. Or we could get a 1 and a 4. So the size of this event space is 1, 2, 3, 4 items. We could have got that from our table, right, to get a 5. 4 ways to do that. Plug that in here. Recognize that 36 is just 12 times 3, and 12 is 4 times 3, so the 4s will cancel, and we'll just end up with 1 over 9 as our final answer, which is 0.1 repeating, or 11.1%. Okay, so all the examples that we've considered so far have consisted of sample spaces made up of discrete elements. That is, we can write down each individual element in a list or in a set and then count up how many there were. There are also continuous sample spaces. So imagine a dartboard. Now, if I told you that at a certain distance when you throw the dart, you're guaranteed to land somewhere in this big circle. So 100% probability you're going to hit this circle. So I adjust the distance from the board such that that is always true. And then I ask, what's the probability that you hit the bullseye? How can we answer that question? Well, we'll first need to distinguish. Well, let me just say this. It's obvious to you, right, that the smaller the area of the bullseye, regardless of where it's centered, right? It doesn't matter if it's over here or in the center. The smaller that area, the harder it is, the least likely it is that you're going to hit it, right? Does that make sense? If it was as big as the whole target, and I already told you that you're close enough, you'll always hit the target, right? Then you have a 100% chance of hitting the bullseye. But if it's teeny tiny, that's going to be harder, right? So you can see there's this correlation between the probability of hitting the bullseye and the size or the area of the bullseye. And so if I designate that this bullseye has a radius of little r, that's a really tiny r, I apologize, let me write it a little bigger. R. And then of course we have our dartboard size, big R. Recall from, I don't remember what lecture it was that we did circles, but it was fairly recent. The area of a circle is just pi r squared, so the area of the dartboard, which I'll write like this, board, is equal to pi big R squared, and the area of the bullseye, which I'll write as bulls, is equal to pi little r squared. And it kind of stands to reason, if you think about it, that the sample space size, since any place on the dartboard is equally likely, is going to be equal to the area of the whole dartboard. Okay? Because like I told you, you're guaranteed to land somewhere in this board because I've adjusted the distances accordingly. And then the way that we characterize the size of the event space is just simply the area of the bullseye. So the desired outcome is to get a bullseye, and the size of that space will be equal to pi little r squared. So the probability of getting a bullseye, well, I guess I could write it in the same notation that I've been using. The probability of a bullseye is equal to pi little r squared over pi big R squared, which will reduce to just R squared over big R squared. Yeah?
Yeah.
So let me just give you one to try. If use this formula, and let's let little r be equal to, I don't know, we'll just make it equal to 1 inch, and big R, let that be 5 inches. So not a very big dartboard, but so see what we get for a probability of hitting the bullseye using those dimensions. So pause the video, come back when you have your answer. Well, in that case, this probability will reduce to 1 squared divided by 5 squared, which is just 1 over 25. Who can tell me what percentage that is? That's 4 over 100, which is 4%. That would be a pretty easy dartboard, I would think. Because I know when I try it, I get a much lower bullseye rate than that. All right, so next we'll talk about compliments. And no, not the kind that, where I say something nice to you, but the compliment, if you imagine a puzzle that's incomplete, you've got some of the pieces in, but there's still some that are not in. The space where you haven't finished, that's the complement of the space that you have finished. So it's the part that you have to add to something to get a whole, you see? So let me kind of set this up with a problem. So imagine that we had a box, and inside this box we had 7 black balls, 2, 3, 4, 5, 6, and 7. 5 red balls, 1, 2, 3, 4, 5. And let's say 3 orange balls, 1, 2, 3. And I want to know, what is the probability of drawing not orange? That's funny, huh? You thought I was going to say, what's the probability of drawing red, or the probability of drawing black, or the probability of drawing orange? So what constitutes not orange? Well, not being orange. So being black, that's not orange. Being red, that's not orange. So we could, if we wanted to, add up the probabilities for all the things that are not orange, and that would give us the probability of getting not orange. But another way to do it is to, it seems like it would be easier to calculate what the probability of getting orange is, right? That we can do pretty easily. The probability of drawing orange. Well, there are 3 orange balls in the box. How many balls total are in the box? We've got 7 black, 5 red, and 3 orange. That's 15 balls. So the sample space size is 15, you see? So the probability of drawing orange is 3 over 15, which is just 1 over 5. And we can use this fundamental relationship, right, this fundamental law of probabilities that the sum of all possible outcomes have to add up to 1, or 100%, to our advantage, because we can say that the probability of getting not orange is equal to the complement, 1 minus the probability of getting orange. You see? Yeah. So now we can easily calculate this, because it's going to be 1 minus 1/5, which is just 4/5, or 80%. Okay? Okay. Pretty straightforward, right? Let me ask you, from a deck of cards, what's the probability of not drawing an ace from a deck of 52 cards? So maybe you need a little bit of insight into what makes up a deck of cards. And so I have a deck here. And the first thing we want to know is we have to discard these cards that don't really participate in the game. The joker cards, I'm not sure what those are used for, and then some extra card advertising something or telling us rules to a game. And so once we've done that, oh, well, look, there's an ace. So if I drew from the top of the deck, I guess my probability is 0 of not drawing an ace. And we see that we have the name of the card and then a little symbol. This is called the suit of the card, okay? And there are 4 suits. The diamonds, hearts, which are also red, and then the black suits are clubs, which look like kind of a 4-leaf clover or a 3-leaf clover, and spades. Okay, so those are the 4 suits. And the cards in the deck, you have an ace, and then a 2, and then a 3, and a 4, and a 5, and a 6, and a 7, and an 8, and a 9, and a 10. And after 10 comes a jack, a queen, and a king. The jack, queen, and king are called face cards. Okay, so that's 13 cards, 4 suits, 13 times 4, 52. Okay, so those are all the cards. And I want to know, what's the probability of not drawing an ace? So we're going to use this idea of complements to solve that problem, or you'll use that. So go ahead and try that at home. Come back when you have your answer. I want you to find out the probability of not drawing an ace. for a deck of cards, the sample space, if I draw any of these cards, how many different cards are there? There's 52. So the sample space size is 52. And the outcome that I'm interested in is not ace. We should use the method of complements to solve this problem by first calculating what's the probability of drawing an ace. Whatever that is, we subtract that from 1, we have the probability of not drawing an ace, okay? So what is the probability of drawing an ace? Well, we need to know how many different ways can we draw an ace. So the event, that is the desired outcomes, would be we either get the ace of diamonds, I guess I could have drawn it in red since I have red, but, or we get the ace of hearts, or we get the ace of clubs, or we get the ace of spades. So the size of that space is 4. There are 4 different ways that we can draw an ace. Yes? That means that the probability of drawing an ace is 4 over 52, which is the same thing as 1 over 13. Yeah? So the probability of drawing not ace is just 1 minus 1 over 13, which is 12/13. What does that come out in percentage? 92.3%. So pretty likely you don't draw an ace. Okay. In the homework, there'll be plenty of card problems. So you should definitely familiarize yourself with these 2 colors, red and black, 4 suits, diamonds, hearts, spades, or clubs and spades, and the 13 cards, starting with ace, ending at king. So as you proceed through your mathematical studies, you're going to notice that math becomes less concrete and more abstract as you go farther along. And so what do I mean by that? Well, a concrete idea is something like 2 plus 3 equals 5. Okay? Or even more concrete would be 2 apples plus 3 apples equals 5 apples. Okay? Abstraction is where we kind of remove this concrete shell and to get at the essence of it, what's actually going on. We recognize that 2 apples plus 3 apples has something that is the same as when we took 2 oranges plus 3 oranges. It's this idea of 2 plus 3, 2 things plus 3 things. So, but it gets much more abstract than that. And so I want to take a kind of an abstract look on probability. And what I want to do is I want to consider a space. We'll call this the universal sample space. That's the space of all possible outcomes. And let's put in a couple of outcomes in here. And I'm going to represent them by their area that they occupy in that space. Okay? So if it is event A, it lies within this circle in the space of the realm of possibilities. Okay? Then I'll draw another circle, and I'm going to call that B. Notice that these 2 circles are separate. So if you're in the area B, you're not in the area A, yes? When 2 events have that relationship, we call this A and B are mutually exclusive. Okay? Kind of the opposite of that is if they do share some space in common. So here I'll write A, here I'll write B. And you can see that there is an overlap region where some of A is inside of B and some of B is inside of A, right? And we call this overlapping. So for example, the suit of diamonds and the suit of hearts are mutually exclusive. There are no diamonds that are hearts or hearts that are diamonds, right? But hearts and red have overlap. Okay? Because all hearts are red, but not all red things are hearts. There's also diamonds, which are red. Okay? So the area of red is shared by both hearts and diamonds, which I haven't drawn here. It'd be a third thing, but that's the idea. Okay? So in that case, not mutually exclusive. When we do have some overlap, there's some interesting things we can say about it. If I'm only interested in the overlap region, right there, this again is A and this is B, then this is called A and B. This tall kind of triangle without a base is the symbol that people use for and you can remember it because it looks almost like the start of a capital A without the crossbar part, yeah?
Yeah.
Similar, if I consider the entirety of the regions all of A and B and the intersection region, this is called A or B, where this symbol means or. Okay? So for A or B, you can be just in A, you can be just in B, you can be in the overlap region as well. Any three of those is possible. As long as you're not outside of the regions of A and B, A or B is true or satisfied. Okay? Now there's some fundamental relationships here. So the probability of A, and let me just point out that A and B in probability is written like this. So this is the same thing as the probability of A and B. The probability of A and B is equal to the probability of A plus the probability of B minus the probability of A or B. That's supposed to be a dot there. Similarly, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So there is a symmetrical relationship there. Okay? So that means that if we know, say, the probability of A and B, and we know what the probability of A and the probability of B are, we can calculate what the probability of A or B is. Okay?
Okay.
So let's try that now in a real example. I'm going to put this over here. So let's use this to calculate the probability of drawing from a card, a deck of cards, either a red or a face card. Okay, remember the face cards, Jack, Queen, and King. Each of those occur in all four suits. And red, well, half the deck is red, the spade or the diamonds and the hearts, and the other half is black, the spades and the clubs. Yeah, I guess I'll let you try that at home, see if you can get the answer. I think you should be able to get through it. If you get stuck, then unhit the pause button and return to the video, and you'll see the answer. So try that now. Come back when you're done. Okay. So fairly sophisticated problem that we have here. But if we take it in pieces and we use this formula that we've got, we want to get the probability of red or a face card. Well, that's this formula here, right? This is going to be equal to the probability of being red plus the probability of being a face card minus the probability of being red and a face card. So we'll take each of these in turn. For starters, the sample space is still going to be 52 cards, right? So we've got a sample space of 52 cards. How about the probability of being red? What's that? Well, half the cards are red, right? Yeah? So that means there are 26 out of 52, or 1/2. We're going to stick with the same base because we'll need it, the same denominator when we work up here. So there's no reason to simplify this as of yet. All right, how about the probability of being a face card? Well, there are 3 face cards in each suit, and there are 4 suits. So 3 times 4 is 12. So 12 out of the 52 cards are face cards. So the probability of drawing a face card is 12 over 52. Yeah?
Yeah.
Now the last one is probably the hardest one. How about the probability of being red and a face card? Okay, well, what do we know about that? We know that half the deck is red, half the deck is black, right? So that means that the probability of being red and a face card must be half the probability of just being a face card, yeah? So this last part, the probability of red and, I can write it in the other syntax, I suppose, comma, face card is equal to 6 over 12. So now we have all the pieces. All we have to do is plug them in. Probability of being red is 26 over 52, plus the probability of being a face card, we got is 12 over 52, minus the probability of being red and a face card, that's 6 over 52. Why did I write 6 over 12? Sorry. 26 plus 12, you can tell me what that is?
38.
38, and 38 minus 6? Louder. 38 minus 6? 32. So that's 32 over 52, which if we simplify that, and we'll find that it's 61.5%. Okay? Yeah?
Yeah.
Okay. All right, the last thing I want to mention, and we're not going to go into any great detail on it, but just the idea about events being independent. So if two events, A and B, are independent, this is not the thing about mutually exclusive or overlapping. This is different. If they are independent, then we find that the probability of A and B can be given by the probability of A times the probability of B. So let's look at a situation where this applies. Let's think of a coin flip, but not just one coin flip, two coin flips. So if you're thinking, what does independent mean? You can think, well, it means that this probability of A does not depend on the outcome of B. Okay, so or let's say that a different way. The event A does not depend on the outcome of event B. That is what makes them independent. So you can imagine that a coin flip, if I first get, looks like I got tails this time, that has no impact on what I'm going to get the next time I flip it, yeah? On the contrary, I guess some people do believe that they're related because they go to casinos and they gamble and they're like, well, I've won every time, so I'm on a streak. I'm going to win the next time. And that's, of course, how people lose all their money. They have a name for that, but I forget what it is. But I suppose it's some kind of confirmation bias. This would tell us that the probability of getting heads, I can't write it like that because that's A and, yeah, that's right. 2 times in a row is just the probability of getting heads times the probability of getting heads, which we already know is 1/2 times 1/2, which would be 1/4. So the probability of getting heads twice in a row is 25%. How about 3 times in a row? What do you think? 3 times in a row? Heads and heads and heads. If they're independent events, then it's just probability of getting heads times the probability of getting heads times the probability of getting heads. That's 1/2 times 1/2 times 1/2 is 1/8. Yeah?
Yeah.
So you can see how repeatedly rolling heads becomes increasingly unlikely, yes? Let me do one final example just to show you some complications that you'll run into when thinking about these independent events. If I want to calculate the probability of getting 2 heads and 1 tail, where the order doesn't matter, right? All I want to do at the end of the day is have, after 3 flips of the coin, have got heads at least twice and tails at least once. This I cannot write as I have before. It's not going to be 1/2 times 1/2 times 1/2 or 1/8. It's actually different because there's more than one way to do this, right? This could look like heads followed by tails, or heads, then tails, then heads, or tails first, then the 2 heads at the end there. You see? Each of these would have a 1/8 probability, but we take them together, right? We have to add them. Remember the additive principle from the combinatorics lecture? So it's 1/8 plus 1/8 plus 1/8. So So we see that the size of this space is 3. The size of the sample space is still 8, right? Because we've got 1, 2, 3. 2 choices for the first one, 2 choices for the second one, 2 choices for the third one. That's 2 times 2 times 2. That's 8. So the sample space size is 8. So this is equal to 3 over 8. Okay? In terms of the independent probability, the independent events we talked about earlier, it's going to be the probability of getting this, right? So this has a 1/8 probability, this has a 1/8 probability, and this has a 1/8 probability. We add those up. That gives us our 3/8 probability that we acquired by calculating it directly. Yeah? So I think that's all that I wanted to cover. There's tons and tons and tons that you can cover in probability. It's a very interesting area. If you're interested in looking into it further, you might look into things like Pascal's triangle, which was actually originally, this was like the first bit of probability math, I think, ever. That was the reason it was invented, for gaming purposes, if my recollection is correct. And more modern stuff, Bayes' theorem or Bayesian statistics. If you follow politics at all, you're probably familiar with, I can never remember this guy's name, Nick something. He uses Bayesian statistics to aggregate many different polls to try to predict political outcomes in elections. But again, it's really not that hard if you learn it, think about it properly. But I guess medical doctors are too memory oriented, and so they tend to be people that are good at memorizing long lists of things rather than thinking analytically, and so their math skills seem to be lacking. But yours won't, because you got a good start here in basic probability, and so hopefully you won't make the same boneheaded mistakes that they've made. They're not the only ones. Astronomers also made a lot of silly math errors in the 20th century. But this is the penultimate lecture, right? The last lecture is the next one, on just kind of an introduction to algebra, just to whet your beak on the kind of ideas that will come ahead when you do algebra studies, if you continue your studies in mathematics, that is. So I will see you next time.